2010, Bart Merci is the director of the International Master of Science in Fire Safety Engineering on behalf of Ghent University. He is also editor-in-chief of Fire Safety Journal. He is a guest professor at several institutes and has won multiple national and international awards, including the recent Arthur Guise Medal by the SFPE Foundation. He is a fellow of the Combustion Institute and a co-chair of IAFSS Working Group MaCFP, Measurements and Computation of Fire Phenomena, and is member of multiple editorial boards and the scientific committees. Today, so let's welcome Professor Bart Merci to give us a speech.
Thank you. Thank you so much, Professor Liu and Nayan. It's a big honor and that you are introducing me. Thank you. Also very happy to be here at USTC, with which I have a long-lasting good relation and collaboration, in particular with Professor Hu Longhua's group, but not limited to that, with many joint PhD students. I see a few faces here, and I would also like to express my gratitude for the tour that I got yesterday in the lab. I've seen many papers from this lab, and it was very good to see the facilities yesterday. So thank you very much for that as well, and also thank you to Professor Tang Fei for being the hospital, such a good host yesterday evening for dinner, and for being a good friend also. So for me, it's an honor and a privilege to be here, and I would like to try and teach something on CFD. CFD is a computational fluid dynamics, and as you've heard, that has been my major area of expertise as a researcher, and still is in the research team. And I'll try to share some thoughts and some vision on how we believe that CFD can be perhaps used to try and have a better understanding of fire dynamics. And I would like to start off by explaining what is so special about fires and why is it not the same as, for example, CFD in other fields, such as wind turbines, to name one, or furnaces, to name another. So what is so special about fire? And I'll then briefly go through equations. I will not spend too much time on that, because that would take hours to fully explain that. But I prefer to then move on to two examples where we will demonstrate how CFD can probably be useful to understand what's going on in the compartment. Fire one will be in a naturally ventilated compartment, and the other one will be a mechanically ventilated compartment. And I'll try to draw some conclusions and give a little bit of an outlook as where we might be going in the future. But first things first, what is special about fire? And I'm not sure that everybody here is fully familiar with CFD. So I would first like to demonstrate or to make clear that CFD is about calculating flows and temperatures and concentrations inside volumes when we talk about the built environment, but could also be in open atmosphere when we talk about wildfires, as is one of the important research topics here as well. So both compartment fires and wildfires. Now, how do we do that? If we take the compartment, for example, where we are, the room where we are, then you subdivide that big volume into many smaller volumes. And this is then called a computational mesh. And in each of these boxes that you create, you are solving the basic transport equations, which I will show later on. But you can see from this image that if you want to be more accurate, if you want to see more detail, you will have to create more boxes, because then you will have a higher resolution. It's like a camera. If you go to more and more pixels, you have more and more resolution. Now, as you refine this mesh, you see that the number of cells goes up quite quickly, because you have a three-dimensional space. So that means whenever you divide a cell by a factor of 2, it's a multiplication of a factor 8 in the number of cells, plus also the time steps that you can take have to be shorter, because then you are solving on a smaller mesh. So in general, rule of thumb, if you divide by a factor of 2, your computational time goes up with a factor of about 16, which is quite important, because if a calculation takes 1 hour and you divide by a factor of 2, it becomes 16 hours, and another factor of 2, it becomes 10 days. So that means you go quite quickly in terms of computational time. Now I put some numbers here. You will see this later on again in the lecture as well. It's a small compartment. It's 3.6 by 3.6 by 2.4, so it's a small room. Now if you go to a 10 centimeter mesh, then it's very quick. It's not so many cells. But if you go to 2.5 centimeter cells, you're already at 4 million cells. And well, you can go higher than that, but honestly, I have never seen a calculation where you go to 1 billion cells, which would be what you get to if you keep dividing by a factor of 2. So I'm just saying this because you see that a typical order of magnitude of computational cells in a compartment like this would be a few centimeters. Now, that's quite problematic, because if you think about a fire in a building or in a wildfire now, wildfires, they could easily cover kilometers in size. A building on fire, if it's a high-rise building, is perhaps 100 meters high. So we talk about cells of a few centimeters, but if we want to go to 100 meters high, we will not be able to afford that. So we have a large fire. A fire could last easily for hours in a building, could last for weeks when it's a wildfire. So we have long duration of fires. Now that is a problem when you look at what we can do in terms of computational mesh in CFD. And for that, I'll take a little bit of time to talk you through this figure. What you see here is on the horizontal axis a length scale, on the vertical axis a time scale, and both the horizontal and the vertical axis are logarithmic. So every step here on the axis is an order of magnitude different. Now if you think about the fire itself, then we are here in the top right corner of this plot. The length scale could be a few meters, up to 100 meters, up to kilometers if it's a wildfire. And the duration, it's expressed here in seconds. A fire is typically, let's say, an hour or so to start with. That's a few thousands of seconds, but it could last for much longer. So you go here to very long durations and very large scales. Now, if you think about a fire, you often also think about flames. You also have smoldering fires, but I'm not going to talk about that. If you think about flames, we talk about chemical reactions, combustion reactions. And these reactions, they can be very fast. And the flames, they can be very thin. So when we talk about here reaction, wrong button. If we talk about chemical reactions, some of the reactions are 10 to the minus 6, 10 to the minus 7 seconds, and in the end it's molecules reacting with each other. So these molecules, they are at the distance of, say, 10 to the minus 8, 10 to the minus 9 meters. So orders of magnitude different. Now all these phenomena that you see over here, if you think back about this representation, all of these things happen inside these boxes. And these boxes are a few centimeters large. We talk now here about much, much smaller length scales, very, very fast. So you cannot resolve that. You will have to model that because you cannot see it. It happens inside these boxes and you don't have information of what's happening inside. Now, this is the chemistry and the chemical reactions. Now, fires are also turbulent. Why? Well, because fires are relatively large. And the moment that fires grow large, they will develop turbulence by themselves. Again, that would require an additional lecture to explain that, but please trust me on this, and fires are turbulent. You can also see that. If you have a campfire, for example, you see that the flames are dancing around. That is turbulence that you see. And these are turbulent fluctuations in the flames. Now, the ones that you see are, again, in the order of magnitude of a few centimeters large, because we see them with the naked eye, and the frequency is a few times per second, and so these would be in the order of magnitude here in the scale of perhaps around a tenth of a second. But these are the large turbulent scales. Those are the ones that we see. Turbulence also has a wide range of length scales and time scales itself. And so the smallest length scales and the smallest time scales, again, in turbulence, we will not be able to resolve on the computational mesh. That's why we will be happy to only resolve the large turbulent structures. Now, a turbulent structure in the literature is called an eddy. And so we will have large eddy simulations. If you see the term large eddy simulations, it means that you are following, you're tracking the largest scales. But again, you will have to model a large part of the turbulence that happens inside these computational cells. Ideally, you make your mesh such that you resolve about 80% of the turbulence. That is ideally. In fires, it's very often impossible to do that because, again, we will have to work with relatively coarse meshes when it comes to turbulence. So it means that essentially you will have to model almost all of the turbulence, or at least a large part of the turbulence, and you will have to model all of the combustion that is taking place. Okay, that's because we have to deal here with these large fires, and the long duration and the large size. And that is quite different from, for example, turbulent combustion. In the turbulent combustion community, they can resolve more of the turbulence, they can resolve more of the combustion than what we can do in fires. And that has an impact on the models. And then there is also here advection. Advection, some people call it convection. That is, for example, the smoke motion. If you have a flame, the smoke will start to move due to buoyancy, due to forces in the flow. Again, relatively large scales, but these are normally quite well resolved. And with the computational mesh, we would be here in the order of magnitude around here. So pretty much all of this would be resolved. We don't need special models to deal with that. Okay, so that's the overall setting. So the thing is now that in fires, and that's another difference from, say, a combustion device, in fires, everything is very strongly coupled to each other. If you think about the combustion device, take an engine, what you would have is a team of engineers and they would optimize a certain design, and that optimization would often be that you have good mixing of fuel and oxygen and that you have very efficient burning. In such circumstances, the flame is the result of the flow field, and the flame is relatively passive. It is where it is because of the designed flow field. A fire has not been designed to happen, and everything happens naturally. And now the flames are actually an important driving force for the flow. That again has an important consequence because I've just explained that we will have to model the turbulent combustion, but the turbulent combustion has a big impact on the flow field. And so if you make an error in that modeling, you will make an error in the flow field and you will keep piling up errors. So there is a lot of, say, importance in having a good model for the turbulent combustion. So that is different from a combustion device. We will always have an important impact also of the geometry where the fire is taking place. Take again the compartment where we are now and the situation as it is now. We have a number of doors. That one is now open, right? If there was a fire over here, what would happen is the fire would create the buoyancy, the flow would start, and essentially at some point the smoke, if we don't do anything, the smoke would flow out through that door and fresh air would come in through that door. It will create a certain flow field here inside. But just as well, that door could have been closed and the door in the back could have been open. That would have created a different flow field. So the geometry will always have an impact. If that ceiling had been 2 meters higher, again, we would have a different flow field and a different evolution. So the geometry is always important. And also, that comes along with ventilation conditions. Because fire needs oxygen. If you have limited ventilation, the fire might die due to lack of oxygen. If you have more openings, the fire might grow in a different way. And then also wind will always play an important role. I know there is a lot of research here going on about crosswinds in pool fires out in the open, which is, of course, very valuable, but also inside the compartment. You will have this kind of cross flows, which could become very complex, and I'll actually show an example later on. Another issue with fires that is quite different from, say, classical turbulent combustion is we will have turbulent combustion. The fires are large enough to be turbulent, but close to the burning surface, the flow will not be yet fully turbulent. It will be laminar, quasi-laminar, so not yet fully developed turbulent. And that's a problem, because most of the turbulence models assume that you have fully developed turbulence. Now, you could say, well, if it's okay for the large part of the flame, what's the problem? Well, the problem is that close to the surface, you want to have a good idea of the heat transfer. because that's where the pyrolysis is taking place or where the evaporation is taking place in case of a liquid fuel. So you have to have a good description of phenomena happening close to the surface. And that is what inspired us in Ghent to work with a dynamic approach, which I will explain in a minute. We're almost there with the things about fires. Something that is also quite specific is that the velocities are relatively low. We talk about a few meters per second, in extreme cases, perhaps 10 meters per second. I'm not talking about wind now. I'm talking about flames and flame-induced flows. Again, that's a bit more technical. If you have low velocities, you have also lower velocity differences, velocity gradients in physical space. And again, most of the models that are used in the turbulent combustion community have been developed for so-called jet flames, where you have much higher velocities and much higher gradients, dissipation rates, strain rates. So again, many of the models cannot be just taken off the shelf and be used in fires. Now, where does it bring us? So what you see here at the left-hand side is a sketch that I copied from the book by Carlson and Quintieri. Right-hand side is a scheme from our own book. But what you have here is a burning surface, could be liquid, could be a solid. You have a release of combustible gases. They mix with air from the surroundings to form flames. The flames create a high temperature zone. High temperature means low mass density. You have buoyancy, and you have an upward rising of the smoke. Now, if the smoke rises, and you can think of this as a piston. It's not the same, but then you can think of it as a piston. If you have an upward moving piston, you create an underpressure here. So you have natural entrainment of the air. So this is a natural process. You have the combustion in the flames, generation of heat. Most of the heat flows away with the smoke, but some of the heat is transferred back to the vaporizing or pyrolyzing surface by convection, by radiation, and you have a closed loop. Now, the point that I want to make here is that all of these things are connected to each other. And so if you make an error somewhere in this picture, you will affect everything that's happening. Imagine for a moment that you are under-predicting the heat transfer to the surface for whatever reason, maybe convection, maybe radiation, maybe the flow field, maybe the location of the flame. Imagine that you are under-predicting this, then what will happen is you will under-predict the release of these combustible gases. You will make the flame weaker, you will keep under-predicting the flame, and you make an error that is piling up. Or vice versa, if you over-predict the heat transfer, you will release more combustible gases, you will make the flame stronger, and you will keep increasing the heat release rate. So this is quite important. We have now a so-called non-premixed flame. What does that mean? Well, if you have here the release of fuel, and this is not mixed with air here when it's leaving the surface, and it can only burn as it mixes with air, so that is called non-premixed combustion. I've already mentioned the second bullet point, so I'm not going to repeat that. And a final point here that I want to make is that also in fire flames, the temperatures are relatively low when compared to flames in combustion devices. Once again, fires have not been designed to happen, so it's not optimized mixing. There is much soot production, there is much radiation from those flames, so those flames lose a lot of heat to the surroundings. Yeah, and so the temperatures are relatively low compared to combustion devices, which again means that many of the chemistry schemes that have been validated and developed for turbulent combustion in engineered devices are not directly applicable. And this is particularly true for the formation of carbon monoxide, which is important to know because that is an important killer in fires, and also for soot. So many soot mechanisms are not directly applicable. So many problems, right? Many problems that we have to address. It becomes more complex if you have a fire inside the compartment, because now, as I said before, most of the heat is going away with the smoke. But if you have a compartment with a ceiling, then that smoke does not escape. The smoke is blocked by the ceiling. It will form a smoke layer that will also participate in this entire complex heat transfer mechanism. And so the scheme becomes even more complex than before. Okay? Again, I'm not going to go into more detail here. That about the context, and I know I took some time, but I think it's important then to have that first in mind, and so that you can now perhaps appreciate what we try to do in terms of modeling. So, what do? We cannot resolve everything, we have to introduce modeling, and it was already mentioned at the introduction. If you're interested in looking what people are doing today in terms of CFD, I would invite you to have a look at the MaCFP workshop series, which is a working group under the umbrella of IAFSS, of which Professor Liu is the current chair. And there you can see what the different teams are doing. It's a GitHub database, you find a lot of details. But to summarize, actually what everybody is doing in the fire community is LES, and large eddy simulations, and you resolve the largest turbulent structures. Now what we do in Ghent is something quite unique at the moment, and we'll see if people will follow that, but we use a dynamic approach for the turbulent combustion modeling. What does that mean, dynamic? It means that we do not fix model constants. We make those model constants into parameters, and we give them values that depend on the local flow conditions. And the reason for that is that we appreciate that the flow is not fully developed, so that means that the turbulence is not fully developed, so that means that model constants that have been developed under the assumption of fully developed turbulence might not be valid, and we want to give them a dynamic value. If you do that for turbulence, why not do it for combustion as well? And why not do it for radiation as well? So that is the approach that we are now constantly and consistently applying for turbulent combustion with radiation. And so far, we're very happy with the results. Otherwise, we would have abandoned that route, because it reduces also the sensitivity to the computational mesh. Remember what I showed you, these different meshes? Well, the results will depend on the choice of mesh, but if the result is not very sensitive to that choice of mesh, that is a big advantage in CFD, because that can give you some confidence and that it's a reasonably good approach. Combustion modeling, we use the so-called eddy dissipation model, eddy dissipation concept approach here in the simulations that you will see with infinitely fast chemistry, and that is the most popular approach in fires. What that means, infinitely fast chemistry, is that you assume that the chemistry is much, much faster than whatever happens in the flow, which makes sense. If you looked at the initial diagram, the timescales are indeed shorter, but it also has disadvantages, because if you assume infinitely fast chemistry, it means it will react immediately, even if the conditions are perhaps not good enough for reaction in reality. So we also talk a bit about finite rate chemistry. Okay, I'm not going to talk about pyrolysis, I'm not going to talk about evaporation. Those are very important things to consider, but don't have time to do that. I'm going to go a bit faster here. The only thing I want to mention here for the infinitely fast chemistry is that you are ignoring the chemical kinetics, which also means that it's difficult to predict minor species. Minor species means here in terms of concentration. So for example, carbon monoxide is called here a minor species, but it's actually an important one, and because it relates to the toxicity of smoke. All right. The equations, I'm just going to show them. I'm not going to explain them at all, but basically what you solve is the conservation of mass, the conservation of energy, so the basic laws of thermodynamics. You solve the fluid mechanics equations, which express momentum, it's also known as the Navier-Stokes equations, and you solve transport equations for different species, the different chemical components, which is a convection diffusion equation with a source term. And you make a number of assumptions. For example, here in these simulations, we do not worry about differential diffusion. If you had hydrogen as a fuel, then you would have to look into that, because hydrogen diffuses much faster than other gases, but that's not the point here. So we use this dynamic approach. And once again, I'm not going to guide you through all the equations, and that would again take too long. But what I would like to stress is that if you have a large eddy simulation approach, you also have to model the things that you don't see on the mesh. The things that you don't see on the mesh happen inside the cells, and that is called subgrid scale in the literature. So SGS means subgrid scale, so everything that happens inside the cell. And basically what you want to have there is you want to know how much kinetic energy is in those cells, and that's the subgrid scale kinetic energy. So that's the kinetic energy of the turbulence inside the cells, and also how quickly does the turbulence disappear. There's the so-called dissipation rate. Now for that, you have expressions, I'm not going to explain that, and you have model constants. So you have Cs, you have Ci, you have C epsilon. And if you look here in this table, these are numbers that you find in the literature. And it's quite a wide range. And that's not a coincidence, because if the turbulence is not fully developed, you will have different situations and you will have different numbers. So rather than picking one set here, we now do that dynamically. Now what does that mean? Well, I'll come back to that later. But what that implies is that you also have a direct impact on the turbulent combustion. Because a very important factor here in the turbulent combustion model is the mixing timescale. And the mixing timescale, that is something that results from turbulence. So the turbulent timescale, the time that is linked to turbulence, is going to be used to characterize the turbulent combustion timescale. What that means is that you assume that the combustion reactions themselves are much faster than the turbulent mixing. Remember, non-premixed combustion, they have to mix before they can burn. The assumption here is as soon as they are mixed, they burn. So then you have to make a decision on what that would be. You compare a laminar timescale with a turbulent timescale. Many choices to make here, but long story short, it's the turbulence that determines the timescale for the chemistry. So that brings me now to this plot, which again, I'm not going to explain in all detail. If you are interested in details, I'll be happy to discuss in length. But what you see here are expressions for turbulent timescales normalized with the so-called integral turbulent timescale at subgrid scale. And you see there are a number of timescales, but the important one here is the red line, which is the one that stems from the turbulence model. Now, you see here three plots, and the left one here is for the value C epsilon equal to 1, which means a fully developed turbulent flow. If you have here a weakly turbulent flow, the C epsilon is equal to 0.1, which could happen close to the surface. You see that this red line has been shifted quite far down here in this plot. And then you can have intermediate situations as well. So what you see is, depending on the choice that you make on C epsilon, you will have relatively different turbulent mixing timescales, so you will directly impact the turbulent combustion. Which one to take? Again, impossible to say in advance, which is why we do the dynamic approach. So that automatically the software tells you which value is a reasonable value depending on the local flow conditions. You do that with dynamic filtering. Again, I don't have the time to explain that in all detail, just want to give you a feeling that this is what we do dynamically. Now, this was with infinitely fast chemistry. If you want to also look at extinction phenomena and ignition phenomena, then you can no longer assume infinitely fast chemistry. You will have to introduce a new model. One model could be based on a critical flame temperature. So that you say, as long as the temperature remains below a value, you have no reaction. It could be based on the Dampköhler number, which is a ratio of the flow timescale to the chemical timescale. But you could also think of doing finite rate chemistry and try to let the chemistry predict whether or not you will have extinction or not. If you want to do that, then we work with the so-called eddy dissipation concept, where you introduce here also some finite rate chemical kinetics. Again, many choices to make, many versions on the market. If you take the limit here for infinitely fast chemistry, it becomes similar to the eddy dissipation model with a different time scale. Again, would lead too far. Now, more recently, we are actually not necessarily very happy with the eddy dissipation concept approach, because also that EDC assumes fully developed turbulence. So Professor Snigirev, who has been in the team for more than a year, has developed a new subgrid scale combustion model. And if some of you will be in Milan at the Combustion Symposium, I invite you to his talk, because there he will explain how we do this now in his work. And then you combine it with some finite rate mechanism. There are, again, many in the literature, not too important here. Radiation, I'll go even faster. Radiation is very important, but I will not spend time here today to talk about that. The simplest approach is to work with a so-called radiative fraction, where you have a certain heat release rate of the fire, and you assume that a certain fraction is lost into radiation. But also here, you can go much more complex, because that radiative fraction might not be known beforehand. So once again, you can now solve an equation with emission and absorption. You can make those length scale dependent, and there are expressions for that in the literature, as you see that over here. And then the path length is an important quantity. It appears here, it appears there, and you can prescribe that, or you can make that again dependent on the flame shape. You know, the V here stands for the volume of the flame, and A is the area of the flame, and then you can do that again in a dynamic way. But allow me to go a bit faster so that I can go into the examples. And so also here, I'll go more quickly. Just as a reminder, if you look at the extinction and reignition, you can have three ways of extinguishing a flame in fires. One is the aerodynamic approach, which is what you do if you have a candle. And if you blow out a candle, basically what you do is you create high strain rates in the flow, a lot of heat losses. It's called aerodynamic quenching. So a high value of conditional scalar dissipation rate. You can have thermal quenching, which means that the flames are getting too weak because they lose too much heat, and then the chemistry no longer continues. Or you can also have dilution, where gases are being mixed, combustion products come in, too little oxygen, then you might have also quenching by dilution. So you can deal with that through a critical flame temperature or through a Dampkeuler-based approach. Quite a number of options in the literature again. Also here again, Professor Snigirev worked on that a long time ago, where he worked with the perfectly stirred reactor approach. More recently, also Dr. Dorofeev from Global developed a framework on mixed eddies based. One thing that is in common for many of the approaches is that it's not so easy to avoid what is called spurious reignition. And spurious reignition means that you have reignition of the flame somewhere where you would not expect it. And so there is quite a bit of work to do on that. What we are trying to investigate at the moment is to see to what extent finite rate kinetics can help with that, to what extent this novel subgrid combustion model might help with that. If you want to read a bit more detail, there was a presentation at the Combustion Symposium in Vancouver. You find the link over here, where I give a little bit of an overview in the literature of the different approaches on this. But let's go into two examples. And so let's first go into a naturally ventilated compartment. These are tests that have been done in the US at the Underwriter laboratories. You find the details here on the slide. Essentially what it is, it's a compartment. It's the compartment actually that you've already seen at 3.6 by 3.6 by 2.4, and 2.4 is the height. It has one door. In this picture, as you can see, the door is closed, but in some of the tests, the door was opened, so that you have here, the door is not in the center of the room here or of the wall, so you will create a more complex flow. Measurements, temperature thermocouple trees inside, so that you have temperature measurements. Radiation was, or heat fluxes were measured by radiometer and heat flux gauge. Some pressures were measured, but also here a bidirectional probe in the door opening in an attempt to measure velocities. Now it's very difficult to measure the velocities for fire flows in an accurate way, because the velocities are low, so you need a lot of resolution. But also you don't know the direction of the flow very well, because the fire is going to determine the direction of the flow to some extent. So this is always a bit questionable. If you see velocity data in the literature, you need to be quite critical about that. The fire is here located in the center of the compartment, but they also moved it to the back wall, to the side wall, to the corner. Three values of heat release rate. So you see they had like a range of conditions. And that makes it interesting for modelers. If you have a range of conditions, then you can get an overview. Because if you're a modeler, you can tune your simulations. If you are a little bit experienced, then you can tune your simulations such that you have very good agreement with a specific experiment. But it's much more interesting to have a good agreement, maybe not exceptional agreement, but good agreement over a range of conditions, because that means that your models are more robust, that they can handle different situations. So that is the approach also that we try to follow. Some more details, and just here perhaps most important is that there is specification of the thermal boundary conditions. Boundary conditions are always key in CFD because they will determine the final solution, and the size of the door is mentioned here, and it could be opened or closed. You've already seen this picture before, so we tried different meshes, and that goes along with the so-called D-star criterion. D-star criterion tells you that if you have a CFD simulation where the most important characteristic length scale is the size of the fire, that then you need a resolution of, say, 15 to 20 to have well-resolved simulations. 10 is maybe acceptable. So you see that the finest mesh is certainly always fine. The medium mesh here is perhaps a little bit problematic for the smallest heat release rate, and the coarsest mesh is actually not good enough. And that would be the expectation in terms of resolution. Also perhaps important to mention, if it's a large eddy simulation, which is what it is over here, then every instant gives you a different situation, but it's not so useful to look at instantaneous results. It's better to look at averaged results. And here we first calculated 5 minutes to get into steady state conditions, and then another 5 minutes to get to averaged results over the steady state period. Some more details on how we modeled turbulence. This is done with FDS. The previous version, already 6.8 at the moment. We work with FDS, but we also work with fire foam at Ghent University, which is the code developed by FM Global. FDS is a code developed by NIST, which is the most used code in fire safety science and fire safety engineering. Some discussion on the radiation that I will skip now. You can give the details if you want, but that's what it looks like. So you have the start here. You see the ranges of heat release rates at the beginning. You have what you expect. Flames above the burner. The color, by the way, is temperature. So red is high temperature, blue is low temperature. You have the development of a smoke layer. I mean, high temperature is smoke, which goes more rapidly if you have a higher heat release rate. So that is what you would expect. But now it becomes interesting. If you look here at the bottom plots, or also here at the top, you start to see that the flames are kind of pushed away a bit from the burner. They are no longer perfectly here above the burner. They start to tilt. And that's because of the flow field. Because the door is here not in a symmetric position, so you are creating some kind of large-scale vortex, and all of a sudden now you are forcing the flames a little bit to the side. This is one example where you can see how CFD can help you understand measurements in the experiment. Because if you see a situation like this, you would expect a thermocouple tree that is over here to record higher temperatures than a thermocouple tree that is over there, even though they are symmetrically positioned inside the compartment. And that would be very difficult to measure because the flow field is very difficult to measure. And there are more techniques that are now coming into the literature, which is very good, like PIV techniques to visualize the flow. But CFD is definitely a very helpful tool to understand that. So that's just a qualitative image, which I think is always important to begin with. And then you can start to do an analysis, a quantitative analysis. You can look at the smoke layer height, the neutral plane height. You can look at now quantitative information on temperatures and so on and so forth. So I'm not going to discuss that in all detail, but it also allows you to make plots like this, where here, again, as a function of the heat release rate, the top row is the temperatures, the bottom row is the velocities. And I've included this slide just to demonstrate that indeed the fire is the driving force here. You see that if I have a stronger fire, I also have a stronger flow through the door. So this here, the color is high velocity inward, blue is high velocity outward. So you see that the flow field becomes stronger as the heat release rate becomes higher. And indeed, also the flame tilting was more clearly present for the higher heat release rate than for the lower heat release rate. So once again, CFD helps you to understand the phenomena inside the compartment. Because if the flame is tilted, it has an impact on the heat transfer. In this case, we had just one fire source, but imagine you have combustible objects inside, then the combustible objects that are closer to the flame will be more rapid to ignite, and you will have an impact on the evolution of the fire inside. Now, what happens if we close the door? Yeah, so if you close the door, beginning more or less the same behavior. Now, this one you've seen before, so don't focus too much on this one. It's better to look at the right-hand side. What you see now, the smoke layer comes down more rapidly than here, and now also the flames are getting weaker because they are running out of oxygen. So they don't find oxygen anymore. You have a little bit of reignition here for a few times, and then after a while the flame goes. So that means that the extinction model, as it is implemented here, works. Is it perfect? No. If you look more quantitatively, you see that there's room for improvement, but at least in general terms, the flames disappear. So this is the behavior as you would like to see it. And this is state-of-the-art CFD, so we can predict the extinction, we can predict the impact of ventilation, we can predict the impact of the flow field on what happens inside. Second example, mechanically ventilated compartment, and it's in the configuration of an airtight compartment. This is work that was done by Zhuanyi Li when he was a PhD student in Ghent, and he visited IRSN in France. IRSN is the French Institute for Nuclear Safety, and this is the context here. So in nuclear power plants, you have radioactivity. So what you do not want is, if there is an incident, is that radioactive material goes into the atmosphere. So basically what you do is you create an underpressure in the compartments where there is radioactive material so that it stays inside. Now, this is done by making compartments airtight and by mechanical ventilation, and you extract a little bit more than what you supply. So you create an underpressure. Now, the problem is when you have a fire, the fire will create hot gases. Hot gases want to expand, but if it's airtight, the gases cannot expand. So what will happen is you will have an increase in pressure. Now, if you have an increase in pressure, what happens is it's easier to extract gases, but it's more difficult to supply gases. Now, the supply is air, the extraction is smoke. Imagine now that you have less supply of oxygen. What will happen? The fire will become weaker again. If the fire gets weaker again, you will see in a minute, the pressure will decrease and you will have feeding of fresh oxygen. The fire will get stronger again. You will have reduction of oxygen. You will have increase of oxygen. So you can have oscillatory behavior. Long story as introduction, but then this is what the experiments looked like. So you have basically a box, almost a cubic box of about 1 meter in size. Now you have here at close to the ceiling an inlet duct and an outlet duct. The outlet duct is difficult to see. You have again thermocouple trees, some gas sampling probes to measure gas compositions, and pressure was important to measure. We wanted to understand the pressure dynamics because that has an impact on the ventilation dynamics. We worked with gas as fuel. It was not straightforward in terms of safety, but it has the big advantage compared to liquid and solid fuels that we have complete freedom of heat release rate evolution. By turning on the valve of the gas, you can easily change the heat release rate. And so Zhuanyi did here a wide range of conditions, changing how quickly the fire rises, how high the heat release rate becomes, how long it takes, how quickly it decreases. So we have here a number of parameters that we varied. Once again, because we wanted to have a range of conditions, not one specific condition. And the question is now, what does that imply in terms of pressure evolution? Here you see a couple of images provided by Hugues Prétrel from IRSN, where you see ignition of the pilot flame to get things started. This is then the real fire source, steady burning. I took 2 pictures here just to demonstrate that you have turbulence again. So the flames, even though it's the same stage of the fire, can look quite differently. And then when you close off the valve, the fire extinguishes. Now, if you look at the evolution now of the heat release rate and the pressure, this is one typical result. So let me talk you through this. I'll just explain this once. So start with the red curve here, the red dots. That's the imposed heat release rate curve. So the heat release rate here is at the right-hand side axis. It's actually the mass loss rate, but that's the same. So we have here first a period where the ventilation system is activated, but there is no fire yet. And when the ventilation system is activated, you see that you start with some under pressure, which is the goal, because you want to keep radioactivity inside. Now, in the tests, of course, there was no radioactive material, but that's the overall concept. Now, then you see, if you start to increase the heat release rate, that this leads to an increase in pressure. Now, in this configuration, it did not go to overpressure, but it could have. So you have here an increase of pressure. Why? Well, Chuenyi did the entire analysis. You can find the results in Combustion and Flame if you're interested. But essentially what happens is the heat release rate leads to a pressure increase because there is not yet too many heat losses from the walls at the beginning. So you have an injection of heat by the heat release rate and not yet many losses through the walls. Then we keep the heat release rate constant. So not zero, but constant. And what you see is that the pressure starts to relax again. Why is that? Well, the heat release rate stays constant, but now the heat losses start to increase. You have more heat losses through the walls. So you have here a negative term, and the pressure difference compared to the initial pressure difference starts to reduce. So you see that the pressure starts to relax. Well, not yet exactly this value, but if we had waited longer, then it would have been this value. And then when we start to reduce the heat release rate, what happens now is all of a sudden we create a strong underpressure. Why is that? Well, this is a relatively rapid reduction. So now this one goes to zero quite quickly. This one is still there because the walls are still hot, so you still have heat losses to the surroundings. So now all of a sudden you are expecting here a negative number, which is indeed what we see. We have here a strong negative pressure, and then here we keep the heat release rate to zero, and then as the walls are cooling down, the heat losses are reducing, the pressure relaxes back to the initial value. So from a qualitative point of view, we understand what's going on. Now, what was interesting also in his work of Chuenyi's is that he, for the first time, at least as reported in literature, discovered oscillations in this compartment with gaseous fuel. Up until then, people thought it was only possible with liquid fuel because of the impact on evaporation, but actually also with gaseous fuel, you could now see these oscillations. And it's not linked to underventilated conditions, because what you see here in the bottom right corner is the so-called global equivalence ratio, and the limit value is around 1, and to go to underventilated conditions, this is way below 1. So that means that you have a lot of oxygen available. So it's not about underventilated combustion. If you do the analysis of the oscillations, you have a quite unique frequency from a fast Fourier transfer analysis that actually resembles quite well the frequency that was also reported for liquid fuel in this case. So this remains to be explored. I mean, we have not found the final explanation for this phenomenon, but it's interesting that it was observed. Now, why am I saying all this? Well, because, well, actually, I go a little bit too fast now. Let's do it like this. Okay. So what you will see now is movies, results from CFD simulations. Left-hand side is a vertical plane through the admission duct of fresh air, so the inlet duct of fresh air, as you can see from this image, and the injection of fresh air is here. Red color means high velocity, blue color means low velocity, and it's impossible to see from a distance, but you actually see velocity vectors. So you see actually how strong the flow is by the color, but also the direction is going to be visible by the velocity vectors. The right-hand side is a vertical plane, and if you look carefully, you see here a white spot here. That is the plane through the burner. So it's not the same plane. The injection duct is in one plane, the burner is in another plane. I will run the video in a minute. So these are all CFD results, but it goes... Let me go back here. It goes with this evolution. So the first stages, you will not have a flame yet. It's not yet ignited. So you will see the flow field as a result from the ventilation system. Okay? Then we will ignite the burner, and what will happen is we have the pressure increase. So what that implies is that it's going to be more difficult to supply fresh air. I'll talk you through it when you see the video. Then we're going to keep the fire steady, and you will see that it's going to be easier again for the supply of fresh air. Then we're going to reduce the heat release rate, and then you'll see what happens. Okay, so we start. No fire yet. We have the ventilation flow field. You already see some turbulence. And now we ignite here the fire. So you see here, much less air supply. The fire keeps burning, and then so the pressure relaxes. So you see that we have here again also more injection of fresh air, with quite significant turbulence, not only by the ventilation system, but also now because the fire is playing its role. And you have now a complex interaction of buoyancy induced by the flames and momentum-driven flows that are injected through the admission duct. You will also see that the flames are not nicely here vertical. They are affected by the flow field induced by this injection of fresh air. And so this becomes quite, say, complex, say, dancing flames. In a minute, or less than a minute, we will shut off the heat release rate. And once that happens, once you see this disappear, keep an eye on what happens here. Yeah, this disappears. You see here, all of a sudden it becomes much stronger again. That's because of this strong under pressure, and then it relaxes to the initial situation. And where also here, I did not mention that at the beginning, but you already have a complex flow field with crosswinds, very much alike crosswinds in pool fire out in the open from the early stages. Now, this would be extremely challenging to visualize from experiments, because you do not have optical access into this box. You would have to do that plane by plane. It would be 2D images that you would have to combine. So here, once again, CFD plays a very important role in understanding the phenomena happening inside this box. So the next few slides are just a few visualizations and to demonstrate or to highlight what I've discussed. So this is the situation where we just have the ignition of the flames. So quite vertical flow field here and reduced supply of air. And that's a little bit later when we have still the steady burning, but now this has recovered. So stronger injection with a direct impact also on the flow field above the burner. And then when we switch off the burner, all of a sudden here we have a very strong increase in supply of fresh air, and that's it. Just wanted to add here also again, and you see many turbulent structures, and so this is a quite complex flow field. So this brings me to the closing of this lecture, and so I've tried to explain what is the specific context if you do CFD in fire simulations, and that there is a very strong interaction between the combustion processes, the turbulence, the heat transfer, and the flow fields in general. We believe that detailed insight into the flow field is important to understand the compartment fire dynamics, and at the same time, it's not easy to measure. So that's why we believe there is potential in the use of CFD in fire safety science research, and certainly also in fire safety engineering for the same reasons. We believe there is a lot of potential in the future as well, in particular when buoyancy is not the only driving force. So here we always had relatively small compartments, and the fire was a dominant factor, but you could also have larger open plan spaces where the fire might be moving around. That will create, again, complex flow fields. You can have configurations where the wind is important, large open plan fires, and you can think of many more. Extinction modeling, reignition modeling is not straightforward. So this is something that I think will require still years of research to come up with a reliable answer there. I did not discuss mixture fraction-based models today for combustion, but they might be worth looking into. There are issues there as well, because again, low scalar dissipation rate makes the integration not straightforward and can lead to issues of not recovering the heat release rate as you thought you would get from the inlet boundary conditions. Thermal quenching is important in the fire, so radiation soot will be research topics for the coming decades, and we still believe in that the dynamic approach for this could be an appealing one to follow. So I'd like to end by acknowledging everybody who has ever been active in the research that I've presented today, but in the research in general and the funding agencies, but also a particular mentioning of Dr. Yorios Marachkos, who is the postdoctoral researcher in my team with more than a decade of experience, and he actually also created many of the results that you've seen. And I would like to thank you again for inviting me for this lecture and all of you for your attention. Thank you very much.
Okay, very good talk with a 1 hour, and so I think the talk covers many aspects of fire problems and also many kinds of fire scenarios. So I think you can have many questions to interact with Professor Bart Merci. If that is
happy to take questions.
Just like a lecture. Okay, please.
Thank you for a great presentation. I'm studying CFD more than 20 years. I want to question about the future of CFD with fire. What should we do next 10 years and also 20 years for CFD, for fire study with CFD? What do you think of this kind of topic? For example, I think something like, well, already we can do fire simulation. As we can see, your CFD results are very good. Mm-hmm. So what should we improve? What should we do next 10 years and also 20 years? So if you have some plan, can we show us the future plan and what should we do?
Yeah. Well, I think thank you for that question. I think most of it is on this slide, actually, of problems that are still coming our way. So what we have not yet fully mastered is a good representation of extinction phenomena and potential reignition phenomena. This will become extremely important, I think more and more important, when we talk about underventilated compartment fires. And with modern building styles, where we have a lot of thermal insulation and also buildings with less leakage than before, this will become more and more of a practical issue. Radiation soot will be there for a very long time, and we still have not developed models, I think, and that are generally applicable. But I think we will also be forced by new developments in society. So think about batteries, for example. I mean, they will have a completely different fire dynamics than the classical fuels, between quotes, that we have been using so far. So I think there will also be a challenge of finding a good balance between resolving enough detail and at the same time keeping things sufficiently general. So I think whenever we will have a development in society that has an impact on fire safety, also CFD will be challenged to deal with it. It's not straightforward today on how to define good boundary conditions or a good fire development for battery fires. To name one example. Also, composition of gases, combustible gases, is completely different from hydrocarbons that we've used so far. So I think there will be things coming to us from the practical point of view that we will have to deal with. But even as of today, although CFD simulations, if you compare the situation today to the situation of 10, 20 years ago, what we can do today in a reliable way is enormous compared to 10, 20 years ago. So we've made huge steps I think, forward, but I think some of them still require further improvement. I think the most or the major challenge will be new configurations, and that we will have to deal with. Another example is photovoltaic panels, which introduce also more complex geometries than what we've used so far. So we will have now inclined surfaces that we did not have so much before in buildings. So we are now, not only we, I mean also here at USTC there is work on that, on inclined surfaces, so that we better understand the flame dynamics underneath such panels. Do we need something for CFD there? Well, I think we can apply CFD as it is, but probably we will also have to have a good model of, for example, flow friction in these inclined surfaces, because now we will have to approximate that as a stepwise approach. So probably there will be room for improvement. So I still see quite a number of fields. And one thing that I have not mentioned, but I think perhaps should also be mentioned, is machine learning. So this is a term, everybody starts to use the term machine learning. In my humble opinion, at the moment, it's not yet straightforward to use machine learning in fire simulations, because the data sets that we have, experimental data sets, and that's not criticism, that's just an observation, are limited. And if you compare that to the field of medicine, for example, where they can have millions of images of a knee, for example, and then come up with some diagnosis for an injury in the knee, we don't have millions of examples in our field. And at the same time, CFD, to use that now as training data, I don't think we can do that at the moment, because we would then need fully resolved simulations of everything, and we don't have that in the context of fire. If you wanted to resolve everything, to train models, we are forced to go to very small configurations and invest all our computing power in perhaps 1 centimeter cube. Well, that cannot be extrapolated to a building, right? So I think there is a long way to go, in my humble opinion. So it's easy to say machine learning, but it's really tricky to do. So that's my humble opinion of what I think we will have to do in the next 10, 20 years with CFD.
Thank you. One more small question.
Yeah.
Basically, what do you think of difference between framing and combustion, and also fire? I mean, we are doing fire study. But yes. What's the difference between framing, combustion study, and fire study? Basically, this is something like extinction and reignition.
Yes.
We can say this is something like a frame and also a combustion study. For example, we can investigate a model using detailed chemistry. This is a frame way, but you are using like a fire model. Mm-hmm. What is the difference between fire study and also frame study?
What study? Fire study and grade study?
Grade. Combustion study. What is the difference between combustion modeling and also fire modeling?
Yeah. Well, so there's a couple of things. So one is in fires, we often do not know the fuel exactly. And so if you have a combustion device, you often know very well what fuel you are burning. So you can have, say, a detailed chemistry model dedicated to the fuel that you are burning. In fires, I mean, imagine the fire starting here. Part of it will be wood burning, part of it will be the polymers burning. It's impossible to characterize the fuel. So that's a disadvantage for fire, where we have to deal with that. That's one thing. And a second important difference is that in turbulent combustion modeling, the classical ones, you would have also typically higher temperatures and higher velocities compared to fires. So many of the models that have been developed for such conditions of turbulence and such conditions of temperatures, based upon which the chemistry mechanisms have been developed and validated, we cannot directly use that in fire simulations. And so which is unfortunate. It would have been convenient and good to just use mechanisms from the literature. Let me just go back here to. I didn't discuss it at all, but now that you asked this question, I'll put the table back on. Yeah, this one. So these are some mechanisms. For example, take the two-step Westbrook and Dreyer mechanism. It's a classical mechanism that is very well known in the combustion community. We used that as it is in fire simulations, and we see very significant deviations in terms of carbon monoxide when you compare it to experimental data. Recent experimental data that was done by Anthony Hammonds at NIST also shows carbon monoxide profiles as a function of height. We're off by a factor of 2. And the reason we think is that the Westbrook and Dreyer mechanism was simply never developed for the low temperatures that we have in the fire flames. And so it's just a demonstration, and this is work by Jerry Attabari from the team, and he will also, by the way, present results as a poster at the Combustion Symposium, comparing these different mechanisms. You see that they have not been developed for fire configurations and fire simulations. And so what we are working on now, and that's again with Professor Snigirev, is to start from auto-ignition data at low temperature and at high temperature and try to come up with kinetics, so updated kinetics using auto-ignition data. So trying to redevelop some of the kinetics and that might fit better in fire simulations. This is ongoing work. But that is also something that I think is a big difference between turbulent combustion community and fire simulations.
Yeah. Okay, next question, please.
Thank you very much for the interesting and informative presentation. So just one quick question. Some of our colleagues in USTC investigate the blue ghosting flame through experiment, which usually appears in the extinction state of the compartment fire. So could you please comment that the FDS is capable of modeling this kind of phenomenon in data?
That's a very good question. So indeed, the blue ghosting flames are again a very specific regime of combustion, and I think it's fair to say that this is not the target regime that the FDS developers have had in mind when introducing their models. So maybe I should explain that a bit. What I mean by that reply. And so FDS has been developed not necessarily with fire safety science in mind, but with fire safety engineering in mind. So that the choices that are introduced as default models in FDS have not been, say, developed per se for scientific research. But the source code is open, it's openly available, so anyone is free to develop their own submodels and to implement their own submodels into the source code. And so what I think, and I do not have experience with simulating the ghosting flames, so I have to be careful with what I say now, but what I think could be done is to develop and implement dedicated submodels that are characteristic and useful for that type of flames. And that will most likely require deviation from the default models, because they have not been developed with that in mind. And so I think in principle, if you think of FDS as a software package within which you can work, I would say yes, it has the potential of doing such flames, but only if you introduced the submodels that are valid within the scope of the regime of the blue ghosting flames. Can you do it with the default models of FDS? My guess would be no. So that I think is a bit more subtle. Yeah?
But I think that I have a comment for the ghosting fire, but I think the most significant difficulty is that it's very difficult to conduct the repeated experiments means that you cannot think of that phenomena as a deterministic phenomenon. So it's very difficult to have the repeated observations of that phenomenon. So how to verify that phenomenon by simulations? Mm-hmm. So I think that's a very, very big difficulty.
Yes, that's an excellent comment. Thank you for making that. And because in CFD, in principle, if you have the same boundary conditions and the same initial conditions, it's not going to be exactly the same result because of, say, random variations in numerics and the turbulence modeling. It's always going to be random. So every simulation will be different. But in principle, you would see more or less the same phenomena if you have the same initial conditions and the same boundary conditions. And thank you for making that point, because if an experiment, if it's difficult to have repeatability, then it's very likely that it's sensitive to details or things that look like details and that you do not even think of. And that is very tricky to include in CFD simulations as well, because you will not have all the details in the CFD simulation. To give one very simple example, I mean, and if you take the example that I've shown, sorry for going on this because I like the comment so much, but if you think about here the setup, well, it's even better to see in the other configuration. Look, this is what it looked like in the experiments, right? We did not include the thermocouple trees in the simulations. They were not there. I mean, we put points there and to have the simulation results at the same position as the thermocouple trees. So intrinsically, we assume that the thermocouples do not have an impact on what happens inside. Actually, you make the same assumption in the experiments because you put the thermocouple trees, and even though perhaps you do not mention it explicitly, actually implicitly you assume that that will not change what happens inside, because otherwise you're changing the conditions inside. Now, I'm mentioning this because particularly when you have a gas sampling probe close to the burning surface, it has been shown that this can have an impact. If you have a probe there, you're changing locally the flow condition and you're changing the mixing of oxygen with the gas. And so particularly when it's difficult to have repeatability, it's also going to be very difficult to find that in the numerical simulations, because there you would also have to introduce those details that have an impact on the experiments in the CFD. How to do that? Well, very difficult, maybe even impossible, if even the experimentalists who know all the details of their setup, if they cannot put their finger on what is it that creates the ghosting flame or not, you can also not introduce it in the CFD simulation. So thank you very much for making that comment, because that is, I think, also a field where we have to learn still a lot.
Especially for the small size of the compartment. So I think that thermocouple trees will have a very significant influence.
Yes, yeah, could be. Yeah.
Next question.
Thank you for your enlightening presentations, and I'm a PhD in USTC. I'm now doing some research in the flame and the combustion of solid, and now I have some questions. First one is, how can we simulate the behavior such as the ignition, piloted ignition, rotor ignition, the flame spread of the solid, and also the solid has so many kinds of solid, and the properties is totally different. And how can we simulate some parameters like critical temperature and flame spread?
Yeah, that's a lot of questions in one question. So let me try to go one by one. So auto ignition. If you think about auto ignition in the gas phase, there you can try to find data in the literature, but again, you would have to focus on the low temperature zone to develop that in fire simulation. Ignition or auto ignition of solids. There again, we already go into strong sensitivity to many details, also geometrical details. So can we simulate that? Ideally, yes. If you can characterize all these details, perhaps yes. But then we come to the next sub-part of your question, which is the material properties. They are not fully characterized. And so I didn't mention it today here, but inside the solid, as you surely know, there are pyrolysis phenomena taking place. Now for pyrolysis, again, if you want to do a compartment fire simulation, you will have to introduce approximations in the pyrolysis model. Because if you want to simulate all the chemistry and all the heat transfer and perhaps moisture transfer that is going on into the solid, you will have to spend so much computing time on that it becomes unfeasible and to have the coupling with what happens in the gas phase in the compartment. So what people often do, as probably you know, is Arrhenius rate expressions with one-dimensional heat transfer into the solid, and essentially you would have, say, a pyrolysis front or region, and that moves into the solid and that releases combustible gases. This is a strong simplification of what happens inside. So, and I'm mentioning this if you now talk about flame spread, which was another part of your question. Flame spread is very complex. It's actually what we love to do because it is so challenging and it's so complex. And Jorgos Marcos is working on that on a daily basis. Why is it so complex? Because it combines everything. So you have the flames in the gas phase, the heat transfer by convection, by radiation in the gas phase, difficult by itself to compute. And then we have the phenomena happening inside the solid. If you want to do a really detailed flame spread simulation, including the pyrolysis phenomena inside the solid, you will have to reduce yourself to limited size samples, again for computing times, but you could do it if you wanted. Again, if you can characterize what's going on inside the solid material. And yesterday, I was guided around in the lab, and some of you are characterizing materials. That is very important work, because you need that as input for the models. So can we do it? In theory, yes. We know which equations to solve, but indeed it's the input data that is missing for the moment. So the real detailed characterization, including kinetic parameters inside the solid, that if you have that, that's a treasure, because that's what people are looking for in the simulation. So the equations are there, the numerical techniques are there, we can do it, but you need the input data. Yep.
Yes, I agree with you, especially for the flame spread. For example, in the fire spread, the models for violent fires, currently you know that we use lots of assumptions. For example, the ignition temperature. Ignition temperature is a very empirical parameter.
Yes.
And also we assume, for example, the shape of the flame front, also the temperature of the flame.
Yep.
So we use the ignition temperature to neglect the details of the chemistry. But for detailed CFD simulations, I think in the future, all these problems will be solved. But it's very difficult.
Yeah, yes, I fully agree. I mean, you are much more an expert in wildfire than I am, but indeed, with my limited knowledge, basically, you go back to the one of the initial plots here, and with the graphs. Oh, here, particularly in wildfires, but you can also think of it in compartment fires. You have to make decisions. So if you want to, is it me? If you want to do simulations over kilometers and days, yeah, you cannot afford to go into too much detail. And then some people are focusing on CFD, including vegetation and characterization of vegetation. That's also fine. It's a different type of simulations. Then that means then you will try to look a bit deeper in what's happening there. But indeed, like you've mentioned, ignition temperature in wildfires, it's more or less the same. If you look here, for example, now in the gas phase, so when I talk about critical flame temperature, that's an empirical number. That doesn't stem from chemistry or detailed chemistry or physics. It's a number that you use to avoid the complexity of the finite rate chemical kinetics. So it's in a way similar to what Professor Liu just mentioned. Yeah. Yep.
Okay. Maybe we'll have a last question.
Thank you for your.
With pleasure.
And I still have a more specific question, which is about the ignition. And I was wondering if we could get the temperature, the critical temperature of the solid, if we have the properties of it, and also the environment circumstance of all these parameters, if we can get the temperature evolutions of it.
Yeah, well, I think if you have, let's say, in an ideal world, if you have all the information, you could see that indeed below certain temperatures nothing much happens, and then all of a sudden it ignites. So it is indeed a quite sharp transition between no ignition and ignition. So you could, from those graphs, ideally, if you had all the information, you could define the critical flame temperature, or ignition temperature. The problem is, I think, that ignition temperature will depend quite significantly on all the details, not only the materials, but also the way you ignite, the way the flow develops as well. All of these things will have an impact, and that makes it a useful, I think, model parameter and input parameter, but also not much more than that. I think it will always remain to a large extent empirical, because the temperature is, say, a global quantity that is the result of many physical and chemical phenomena that take place. And thereby, it replaces all this complexity, but it will become empirical and therefore also configuration dependent, is my take on this.
So the need will be much more easier to get the temperature in this process instead of the critical temperature.
Sorry, I didn't fully understand.
Will it be much more easier to get the temperature evolution in this process, not the critical temperature, ignition temperature? I just want to know the temperature evolutions in this process, not the.
Yeah, I think maybe I misunderstood the question, but if you do an experiment, you have certain conditions, you don't see ignition. You change something, you heat up the sample, and at some point it ignites. Yesterday I saw an example of, say, lightning. So you have an arc and the pine needles ignited. With that conditions, it ignites. If you change the conditions, maybe next time it does not ignite, right? So you can then try to come up with, say, a map of conditions. Here I see ignitions, here I don't see ignition. So if you do that now, if you have, let's say, a range of conditions and you monitor the temperature somewhere, say the surface temperature, for example, of your solid, you could interpret that map as a function of the surface temperature of your solid. And then you could say, well, with this, from this temperature onward, I always saw ignition. Then you could say, this is my ignition temperature. My point is that that map, as a function of ignition temperature, is going to depend on the configuration and on details of that configuration. So it could be a very useful number with that specific configuration in mind, but I think it will be difficult to extrapolate that number for different conditions because it is an empirical number and not something that comes from first principles. That's what I would think. Yeah.
So what I want to ask is, can we know the temperature distribution of all of the solid, including the index and the width and the length?
Well, that will depend on, of course, your experimental device. So indeed, there are techniques perhaps to have surface maps of temperatures. Going in depth is already much more difficult. So surface thermometry has been quite well developed, but going in depth, you have to be intrusive. You have to put thermocouples probably, and then again, you're changing what happens inside the solid. So I think that for experiment, that's easy for me as a modeler. For me, that is easy. The experimentalists, that's a headache, I think, to have in-depth and surface temperature measurements with a lot of detail, and at the same time not affecting what is going on. It's like the thermocouple trees in the compartment. It's, I think, worse if you have to drill holes and put thermocouples inside the solid, then you're really changing the phenomena happening inside the solid. So I think that is a limitation of where we are with the current techniques.
Thanks for your answering, and that's all.
Yep, with pleasure.
Okay, so is there any question for the last one, especially, I just to say, especially from ladies? Is there any? Please. Yeah.
Thank you for the presentation, and I just have a simple question, probably not that simple. So it's like, I'm thinking about the logic between the experiments and the simulation. So let's say you just said from your model, you can also suggest the distribution of the thermocouple in the experiment. So if we want to design an experiment, do we design the experiment first, and then we use the results from the experiments to do the simulation? Or we do the simulation first, and then we design the experiments? Or that is like an iterative process, so that like our results could be better?
Yeah, that's an excellent question. I would recommend, if you have a certain experimental setup in mind, particularly if you already have a little bit of experience, to run a CFD simulation. It doesn't need to be perfect. It doesn't need to have the excellent agreement with the experiments, but it will give you some insights of what could be interesting regions to consider to put more, say, experimental devices. And I think, yes, it's an iterative process, but it doesn't require too many iterations. If you at an early stage, particularly if you are in the design phase of an experiment, and if you run a CFD at an early stage, you have some idea of where phenomena take place that you perhaps would like to see in more detail, and then you could invest a little bit more experimental device in that region. Thank you for asking that question as well. So if you go back to the first example with the naturally ventilated compartment, let's go here. Yeah. So you see, and this is a logical, say, starting point. If you put the fire here in the center, and you put one here to the left, one to the right, one here, it's all symmetric, right? If you now know the CFD simulations, you know that actually the flames are not going to be symmetric anymore. So it's a pity that there is not more, say, for example, heat flux meters here at this side, because you only have this one, and the flame is perhaps somewhere over here or somewhere over there, and you cannot really tell because you only have one measurement point. So I'm not criticizing, just to be clear, but if it had run, say, a CFD simulation in advance, maybe there would have been, say, an additional heat flux meter over here, because you would expect the flames to be there. So in general terms, I think it does make sense to say try to run, say, a CFD simulation with nothing fancy, just to see what's going on in a flow field and to have an idea. Likewise in solids as well. If you have, say, heat transfer inside the solid, why not run a simple heat transfer model? Doesn't need to be too fancy, and just to have an idea, like, okay, here nothing much happens during the duration of my experiment. Maybe the heat does not penetrate into the entire depth, and then it's maybe best to put some more devices closer to the surface. Or something is happening in the corner and not so much in the middle, or vice versa, and then you need to invest more there. So it's a little bit of a long answer, but the short answer is yes, I think it's a good idea to do that. And if you are in a more experienced phase, I think it also makes sense to run so-called blind simulations. That is something that doesn't happen all that often. And with the approach that we are using now at Ghent University, I would actually be happy to run a number of blind simulations, meaning there is an experimental setup that has been fully developed with equipment, tell us where it is, and we run the simulations without knowing any of the experimental data. That is the most honest thing you can do, because once you know the outcome of the experiments, then you can start tuning. And with our experience, I can tell you that, you know, we can have pretty much good agreement for almost anything. If you just give us some time, we can tune some model parameters and we will get there. But that's not the point. We want to have models, and that's what we have in mind also at Ghent University, not only for the science, but also for the engineering. And so then we want to give a model that is robust, that you can give to an engineer and say, here, this is what you can use, and we believe you will have a reasonable prediction of the outcome of any configuration. Yep.
Thank you for answering.
Yep. Thank you.
Okay, so the time is running short, so thanks again for the very great lecture of Professor Bart Merci.
Thank you very much. My pleasure.